Let's talk about distance now. We have the following problem. A particle moves with a certain velocity, and you're given the velocity as a function of time. How far does it move between time A and time B? Now, if the velocity is constant, that's easy. If the velocity is constant, then the distance is the rate times the time. So you would take the total time, you would take the velocity, and multiply by the time b minus a. Easy. But that only works if the velocity is constant. What do we do if the velocity varies on us? The answer, as you might have guessed, is we integrate. Let's take the time interval from A to B. Let's call it T naught A and Tn B. We'll break the time interval into n pieces. So we'll call this time T1, this time T2. This is Tn minus 1, and this is Tn. So the length of time of each piece is going to be b minus a over n. And we're going to say that the total distance traveled is the distance traveled in the first delta t seconds plus the distance traveled in the second delta t seconds plus the distance traveled in the third delta t seconds, and so on, plus the distance traveled in the last delta t seconds. So we've taken this big time interval and we've broken it up into little pieces. And now, if we have a particular interval here, so we go from time ti to ti plus 1, we say, how far do you travel in this little bit of time? Well, if it's a really short time, then the velocity here is almost constant. It doesn't have enough time to speed up or slow down very much. And so we pick a time in the middle, call this ti star, and we say the distance traveled between ti and ti plus 1 is going to be the velocity, and that's approximately v of ti star times the time. So velocity times time equals distance, and over this really short interval, the velocity is practically constant. That's the advantage of chopping things up into very, very, very small pieces. So we get that the total distance is approximately the sum, as I goes from 1 to n, of v of ti star times delta t. And if you want to know the exact distance, you take a limit. The finer you slice things, the less ambiguity there is about what your velocity is. Your velocity won't change very much if this is a very, very short time period. So this is the limit as n goes to infinity of the sum of v of ti star delta t. And we have a name for that. That's called the integral, and it's the integral as t goes from a to b of v of t dt. So, haven't drawn any curves, haven't looked at any areas, but we did get an integral. We had a bulk quantity, the total distance traveled in a whole lot of time. We broke it up to pieces, we added the pieces, we took a limit, and lo and behold, the limit of this kind of sum is by definition an integral. So in particular, if the velocity happens to be t squared, then the distance traveled between time 0 and time 1 will be the integral from 0 to 1 of t squared dt. That's almost exactly the same integral that we had for the area under a parabola. The only difference is that now we called our variable t instead of our variable being called x. But it's the same integral which you approximate by the same sums. It's the same problem. Doesn't matter whether it's area or distance. You slice it, you dice it, you add, you take a limit, you get an integral.